Thank you. So with this, we'll continue the theme of cavity-based sensing. In this case, the cavities aren't necessarily going to be doing the sensing, but very much helping out. Excited to introduce my postdoc advisor, current postdoc advisor, Holger Mueller, who will talk about high-intensity cavities for electron microscopy and also the molecular traps.
Thank you. Postdoc advisor, is there anything I need to know?
No.
High intensity cavities for electron microscopy and molecular traps. So the first part is the electron microscopy, and we've already heard that electron microscopy is suffering from two ends. On one hand, specimen give bad contrast and therefore bad signal to noise ratio. On the other hand, the electron beam, as it collects the image, is burning away on your specimen, which means you can't just increase the exposure and get your signal to noise that way. Therefore, in 1959, Richard, this is a physics talk, right? So there needs to be a Feynman quote, says the best way for physicists to help biologists make more progress is to make the electron microscope 100 times better.
Here in Zoom, we need to adjust the microphone. We have to double check it's switched on.
Okay, it is actually not switched on. Is it working now? Yes, it is. There are so many microphones here because so I hear my voice reverberating, and therefore I didn't notice that it wasn't on. So there are two basic applications in molecular and cell biology. The first one is single particle cryo-electron microscopy. That means you purify a specimen. Now you have a bunch of molecules, all of the same type in a specimen, and you freeze them at the temperature of liquid nitrogen. And these molecules inside the specimen have random orientations, at least hopefully, and therefore one image of them contains thousands of copies of the same molecule, all under different orientation, and then the computer can take all these images and put them together to a tomogram using the so-called Fourier slice theorem, which is amazingly elegant. This is the fastest growing method to get at the structures of biological macromolecules, as you can see here by the plotted number of depositions to the protein database. Even structures with a resolution of better than 4 angstrom are now generated. That's the good news. The bad news is the majority of all human proteins is still too small to be reconstructed that way, and that list includes a long list of potential drug targets. So by improving this, maybe one day you can make somebody healthy. The second application is cryo-electron tomography. While electron microscopy shows you the proteins in an isolated state, electron tomography takes a slice of a whole cell. That's one of the amazing things I learned about electron microscopy. A cell is way too large to stick into the electron microscope. You have to use a focused ion beam mill to cut out a small slice. And that slice is then imaged under a series of tilt angles. And again, using the Fourier slice theorem, a tomogram is reconstructed. And that shows you the molecules in their natural biological context so that you can study their functions and vital interactions. Why is that so hard? On the right is an example for the raw data. The contrast is bad. We know why. Specimens are made out of light atoms, carbon, nitrogen, hydrogen. They have weak electron scattering cross sections, so there's virtually no amplitude contrast. Radiation damage forbids you from cranking up the dose in order to get a good signal to noise ratio anyway. And in tomography, you have to cut the already too small dose into a number of tilt steps. So that is extremely difficult. In optical microscopy, imaging weak phase objects is a solved problem. You use Zernike phase contrast microscopy. So how does that work? This is a very rough schematic of the electron microscope. There's an electron source on top. The beam goes through the specimen in the specimen plane. It goes through the objective lens. And then if you assume for a moment that there wasn't any specimen, the beam would come to a focus in the back focal plane of the objective lens. But there is a specimen, and the specimen now acts as a sort of diffraction grating and scatters part of the electron wave function into all directions. So surrounding this bright spot of the undifracted beam, there is now a diffracted component of the beam, which is essentially a Fourier transform of the structure of the specimen. And then the projection optics brings these two parts to interference. So you can view the operation of any microscope as an interference effect between the unscattered and the scattered part of the beam. Putting a bit of math to it, the incoming electron beam is a plane wave e to the ikz, and the specimen is a weak phase object. That means it applies a small additional phase shift I phi as function of x and y to it. But since that additional phase shift is small, the second exponential can be Taylor expanded to 1 plus I phi. The electron detector cannot see phase shift. It can only see the absolute square of the wave function. The absolute square of that wave function is identically 1. That's why there is no image contrast. If you could take the 1 over here, and that kind of represents the undifracted component of the electron beam, and phase shift it by 90 degrees, then the 1 plus I phi is changed to an I plus I phi. And if I now take the absolute square, I get a first order effect of the phase shift and therefore maximum contrast. With phase contrast microscopy, I'm in principle able to extract all the information that a weak phase object applies to the electron beam and turn it into visible image contrast at the standard quantum limit. Okay. People have tried that before, and they have put a thin carbon film into the backfocal plane. The electron beam at the center will charge the carbon film, and that turns the carbon film into a phase shifter, but a highly irreproducible phase shifter. So when the phase shift happens to be the right one, it takes gorgeous images, as you can see here. But the phase shift scatters all over the place during the time it takes to take a data set, and that is not acceptable for biological research campaign. Therefore, few groups have used this with success. There's also electron loss and a still unexplained loss of high resolution information, but I won't get into that. The laser phase plate, the idea now is, let's take a laser beam coming in from the side, focus it on the focus of the undifracted electron beam, and use the ponderomotive interaction between electrons and photons as a phase shifter. The advantage is we don't have to bring any material object into the electron beam. That means there's nothing that could acquire parasitic charges. There's nothing that could suffer radiation damage. The laser beam should obey Maxwell's equations, at least as far as we know, so it should be a well-controlled effect. The problem is we need to focus 75 kilowatts of laser light onto an 8-micron spot in order to get the intensity needed to apply a 90-degree phase shift to a 300 keV electron beam. To put that in context, on the left is a 10 kilowatt industrial laser that cuts through 2 inches of steel without problem. This is big, it's expensive, and we would need 7 or 8 of those. The Department of Defense, of War has a larger laser, but is potentially unsafe and not powerful enough. So you want more laser power, you build a cavity. But how do we design that cavity? We were up to several limits that were unknown when we started this project many, many years ago. Mirror contamination at high intensity could be an issue. We don't really know how bad this issue is. Thermal lensing or local heating of mirrors could be an issue. And finally, the damage threshold of mirror coatings at high CW intensity was virtually unknown. So the idea is the best part is no part. Minimize the number of components that can suffer from any of these effects. Use a 2-mirror cavity. And then in order to get the focusing, it has to be a near-concentric cavity. And that's the first problem. The near-concentric cavity is nearly unstable. In 2016, we proudly achieved 7.5 kilowatt out of roughly 100 kilowatt needed circulating power inside the cavity, which was the highest continuous wave intensity at our focal point at that time. It was limited by thermal expansion, indeed, of the mirror. So the mirror locally gets hot. That means it thermally expands, and that means locally the radius of curvature gets larger, defocusing the laser beam. And so at some point, as you crank up the input power, the focal point inside the cavity gets larger, but not brighter. Later, we were able to trade focusing against NA. So the less you focus the laser beam in your cavity, in principle, that makes the intensity on the mirror higher. And so you could imagine that the heating problem gets worse. On the other hand, the less concentric cavity is much less sensitive to mirror deformation. And so the net effect is you can increase the power if you're willing to accept a lower NA. But unfortunately, that also reduces the intensity at the focal point and therefore moves us away from the intended 90-degree phase shift applied to electrons. So what can you do about that? In those days, our coatings had an absorption of about 10 ppm, but from LIGO, we knew that 1 ppm should be possible. And also those mirrors were made out of standard quartz glass, but ULE material, ultra-low expansion material, should enable us to reduce the thermal expansion by a factor of somewhere between 10 and 100. So those were the ideas that we had. And let me also show you the glamour shot of the microscope in those days. So the central column is a FEI Titan microscope. That's a brand name. It was state of the art when it was acquired by Berkeley in about 2010, but it is no longer state of the art. On the left, you see the breadboard of the beam shaping optics that essentially takes the power of a fiber laser and mode matches it to the cavity. On the right, you see a breadboard for analyzing the spent beam, telling us about the state of alignment of the cavity and so on. The laser itself is a fiber laser in this 19-inch rack, and this eventually goes to a fiber power amp that you can see here. In 2000, when was that? 2017, I believe. Jeremy is here, he did all that. We took first images of the light wave. Okay, so this is not using the laser as a phase shifter to make phase contrast images. This is using the laser as the specimen. You can see on the right how it looks like on the camera. These images are totally unprocessed as they were on the camera. You can see the nice standing wave structure. This really looks beautiful. Was Jeremy's idea to take these images. And we were also able to get initial phase contrast images. So this is not a biological specimen, it's just a thin carbon film. And the phase shift in those days was much less than 90 degrees. So you see a contrast enhancement, but it's not very pronounced. So what if you use more power? And then in 2019, we finally got it up to 90 degrees and beyond. So we exceeded the 75 kilowatt, 300 gigawatt per centimeter squared that we were shooting for by quite a bit, and took images of Rubisco molecules. This is and this is involved in photosynthesis, and 20S proteasome, which is a molecule which has a housekeeping function in cells. So those are not biologically stunning results, but these are results that were the first to really show us that this is working. And from images like that, we got a 3D reconstruction of the proteasome molecules. So this was great. The cavity design, so the whole thing has to fit into the electron microscope, hence the cavity is short. The mirror-to-mirror distance is 20 millimeters. The diameter of the entire metal part is 23 millimeters. The super polish was done by a company named Coastline Optics, which is superb. The mirror coatings were made by 5-9 Optics, which is also superb. And one thing I want to highlight, there's a micrometer screw in here with 400 turns per inch, which as far as I know is made by a one-person company. So what I love about this project is that the manual skills of many people are involved in building this cavity. Anyway, and this is what it looks like schematically installed into the microscope. So the specimen is up there. The backfocal plane is further down, but unfortunately in the proper backfocal plane, that's why I would love to put the cavity, but there's not enough physical space there to install it. Therefore, we use an extra lens known as the Lorentz lens to generate another focal plane where we have enough space to put the cavity. We use that extra lens to our advantage. It magnifies the diffraction pattern about 5-fold, giving us an opportunity to improve the match of the laser beam diameter to the diameter of the undiffracted part of the electron beam. So it's very hard to focus the laser beam to the size of the electron beam in the backfocal plane. And then there's another lens to turn the virtual image into a real image. The power can be stable for 10 hours until you want to go home and turn it off. And theoretical calculations tell you that even though this laser also interacts a little bit with the diffracted beam, which is not wanted, it still has nearly ideal properties as a faceplate. Bragging a bit, the intensity here of 300 gigawatts per centimeter squared is the highest intensity of any laser most of the time in the world. Pulse lasers have a higher intensity, but they are off most of the time. Okay. The radiation pressure at the focus, I think, is 300 gigawatt per centimeter squared, is about 300 atmospheres. And one thing I didn't mention is this radiation pressure is pushing on the mirrors, and there's an optical instability that we had to overcome by locking exactly on resonance. So the pressure is pushing the mirror out of resonance. That means the intensity goes down, the mirror snaps back, and so on. But that anti-damping term is precisely 0 if you go precisely on resonance. Okay, so nice, it works, but there were limitations. Some of them were expected and some caught us by surprise. What do you really want to get out of this? You want to show that you can either reconstruct a protein that is way too small to be accessible with a current electron microscope, or you want to show that you get a better resolution for the same sample, or you want to show that you can get away with taking a smaller number of micrographs, right? Unfortunately, these numbers here are respectable, but they are not a record on any of those metrics, unfortunately. So what went wrong? For one, the extra electron lenses in our microscope cause extra aberrations, and those limit the resolution of the microscope at about 3 angstrom. That was expected. An unexpected thing was we were aware that there's more ice contamination in our old scope, but the problem was much worse than we thought. And the final one was Johnson noise. So let me talk for a minute about that because it was completely unexpected. Whenever an electron beam has to go past a conductor, there are thermal electrons inside the conductor. The conductor is at room temperature, so the electrons move around. And these random currents generate random magnetic fields, deflecting the electron beam slightly, blurring the image slightly. This effect is present in standard electron microscopes, but usually negligible. In our microscope, it was not negligible. First, because of the extra magnification of our extra electron lenses. And second, because the beam hole in the cavity was very narrow, and that means that the beam has to go very close to these metal walls. So the fix was in principle easy, but took several months for the machine shop to manufacture a cavity with a much larger hole. And when we had that, we could show that the contrast transfer function that tells you essentially everything you need to know about the resolution of your microscope is virtually indistinguishable between having no cavity and having the cavity with a large hole. We could also show that the phase shift is stable. Remember the previous carbon film phase plate where the phase shift varies all over the place? Well, that problem is gone. The phase shift is essentially very close to 90 degrees until you decide to turn the faceplate off. We made a serendipitous discovery or demonstration of the power of the faceplate to show you something about your specimen that you didn't know. If you look at these images of so-called apoferritin molecules, Here's a magnified version. The molecules all look slightly different from each other. And this difference is probably just because of damage in this incurred in the specimen preparation. So this is not an interesting biological discovery, but the interesting point is that before phase contrast images, apoferritin specimens were thought of as being nearly perfect. Because in order to interpret standard electron microscopy images, you're averaging lots of particles and the individual damage goes away. With the faceplate, the damage was just so visible that it was no longer possible to ignore. And we hope that very soon the faceplate will reveal biologically interesting variations between the particles. Imaging COVID virus-like particles. So virus-like particles are essentially viruses where you take out the part that makes you sick. But I think these images look so real that you get sick from just looking at them. And again, the contrast between laser off and laser on is quite striking. And then we use the microscope to take images of apoferritin molecules and get a reconstruction, which now goes to 2.8 angstrom resolution, which is exactly where we expect the old microscope to be limited. So at that point, the faceplate was in a state where you would say, well, one step back, one step forward, in the end, it's a wash, right? We're using an old microscope. We're making the old microscope worse by installing extra lenses with extra aberrations, and then we make it better by installing the faceplate. But all in all, what the biologists need is a microscope that allows them to take better data and not a nice physics proof of principle. We were extremely lucky that the Chen Zuckerberg initiative allowed us to build exactly that. So we call this thing Thea. That was the idea of the daughter of a friend of mine. That's the Greek goddess of sight. Thea has a cold field emission gun that generates an extremely monochromatic electron beam, and that overcomes the extra chromatic aberration of our optics. It has a lot of automated specimen handling so that you can go through lots and lots of specimens during a day. That's indispensable for doing biology. It has a spherical aberration corrector. And I'm not going to talk about this much, but the combination of spherical aberration correction and phase contrast essentially allows you to get a flat contrast transfer function out to the highest spatial frequencies that your microscope can image, and that gives you an additional factor of 2 information boost on top of the boost you already get from using a faceplate. Anyway, and it has the most modern direct electron detector camera. We built the faceplate for Thea, generation T1. It worked. We installed the faceplate into the microscope. We are very paranoid to not get dust onto our mirrors. Therefore, when you push the faceplate into the microscope, there's a HEPA filter blowing cleaned air on you, and you're in full clean room gear. And when I asked Peter, well, how do you fit into this box? He says, with great discomfort. But the great thing is, this is an image of gold foil, okay? And then you take the Fourier transform of that image, and so you see these diffraction rings. But this is not running the microscope in diffraction mode. It's the Fourier transform of a real image. You see information out to 0.7 angstrom. That is better than the design goal of 1 angstrom. So this machine would be a gorgeous microscope even without the faceplate. And installing the faceplate did not make the resolution worse. For example, as we've seen before by Johnson noise and so on. So this is 0.7 angstrom with the faceplate installed. And then we took images of various specimens, and the laser on, laser off advantage is fairly plain to see, right? One thing that my postdoc did is you can now plot the spectral signal to noise ratio of those images. And I'm never hesitant to make a cheap advertising pitch. At low spatial frequencies where phase contrast gives you the largest effect. So this is the ratio of the signal to noise with laser to the signal to noise without laser, meaning when this graph is higher than 1, then phase contrast helps. And at low spatial frequencies, where the faceplate gives the largest advantage, it is indeed better by a factor of 100. So we've finally done what Feynman wanted us to do. With that, we're taking images of more and more challenging proteins. And I'll flash a slide, and you are not supposed to ask me questions about that. But it looks like finally, the laser-on reconstructions now have a higher resolution than the laser-off reconstructions. So this shows that it's not just that the images look better by eye, they actually give you a quantitative advantage after you feed them through the data processing pipeline. And
why are we not allowed to ask questions?
You are allowed to ask questions.
That's my only question.
If you're accepting that I might not know all the answers, because this data is brand new and we're still processing. Here is an excerpt from the reconstruction, and you see a nice alpha helix here with the laser on, and with the laser off, it's more blurry, right? So this stuff works, thanks to the Chan Zuckerberg initiative and so on. But I want to show you another application of these cavities, building a universal trap for small chemically stable molecules. So sometimes applying atomic physics methods to a new field challenges us to develop something that you can then bring back to atomic physics. And we want to use the cavities developed for this that do reach very high intensity to make a trap for molecules. Molecules, as many of you know better than me, are interesting objects to trap. I will just cite these reasons. The reaction and collision cross-sections under conditions of low temperature and low density between many molecules are unknown. The rho vibrational structure is complicated, and that means rich and interesting. It can be used in many applications. Cold chemistry is largely unexplored because it's very difficult to get a dilute and cold sample of molecules together for a long enough time to see something interesting happen. And of course, you can use it for spectroscopy and precision measurement. There are several methods to generate cold molecules, and one is buffer gas loading. Buffer gas loading works for a subset of molecules with a large enough magnetic moment, right? But it has a problem that state-changing collisions essentially cause losses and then your molecules again. Dipole traps are universal, but usually limited to millikelvin trap depths, even if you use a 100-watt laser. And that means it's restricted to those molecules that you can laser cool. But we all know that laser cooling molecules is hard because of the complicated rho vibrational structure. So the idea was, can I use the extremely high intensity made by those cavities to build a dipole trap that would have roughly 10 Kelvin trap depth? And that is the case at 300 gigawatt centimeters squared, which we demonstrated as I've shown, right? And then I could load directly from a buffer gas and essentially trap any molecule that will not fall apart at this high intensity. The first challenge was to find, well, are there any? And the good news is that many small chemically stable molecules have their first excited energy levels in the deep UV. So a 1064 nanometer laser is not gonna do much to them, at least in theory. I have to admit that we haven't tried yet, and so you don't really know for sure until you've tried. But then the idea is build a cavity, 1064 nanometer light, pretty much the same cavity as we've already built, but has to be longer by a factor of 4, because we want to fit a buffer gas cell in the middle, and then at the target species would give up its thermal energy to a helium buffer gas at 1.5 Kelvin, hopefully, and then get loaded into pancake-shaped high-intensity regions of the laser beam. Okay. Detection would be through resonant enhanced multiphoton ionization. That's an established method, and for many molecules, REMP schemes, resonant enhanced multiphoton ionization, are available in the literature. We don't have to reinvent the wheel here. Okay. Here's a short excerpt from a list of potential target species. We'll go with nitrogen N2 for now, because it gives a decent trap depth of about 8 Kelvin. The rotational heating rate is benign. Ionization rate is completely negligible, at least if the calculations are right. And there is, as far as we understand, no risk of photodissociation. Photodissociation is essentially getting more and more dangerous as the molecules get larger. And finally, there is a known REMP mechanism for nitrogen N2, so the needed wavelengths and intensities are just in the literature. Okay. These values are fairly typical. So most molecules have trap depth of the order of 10 Kelvin. For the rotational heating rate, isotropic molecules have a very low rotational heating rate. Highly isotropic molecules have a large one. And for those, it might be necessary to go to a longer wavelength to get this rotational heating rate to come down. Okay. And we built our first cavity, and we thought it would just work. So it's 10 centimeters long to fit in the buffer gas cell. But the problem is, at about a third of the needed power, limitations became apparent. So what happens is, as you crank up the power, essentially the power inside the 0-0 mode in the cavity levels off, and any extra power you put in goes into a higher order cavity mode. That was puzzling to us. And then we ended up measuring the output light of the cavity and could indeed see a beat node between the higher mode and the 0-0 mode. So these are indeed resonant modes in the cavity having two different frequencies. And so after a while, we figured out what's going on. The mirror itself acts as an acoustic cavity, similar to what I have heard was reported in the morning session here. So the spherical mirror surfaces form boundary conditions of an acoustic cavity, and inside this acoustic cavity, there are Gaussian modes that would look very much like the Gaussian modes in a laser cavity. Okay. So the laser beam comes in, the radiation pressure is pushing on the mirror surface, okay? And let's say there is a tiny asymmetry in that push. That'll push one part of the mirror back a little further than the other, okay? And then the mirror starts resonating and snaps back. That motion, the Doppler effect produced by that motion, transfers a tiny bit of power into the 0-1 optical cavity mode. And now the 0-1 mode and the 0-0 mode are beating. And this beating modulates the radiation pressure, and you get a self-reinforcing effect if you exceed the threshold laser power for this parametric optical instability. Now, the cool thing about this is there are Gaussian modes in here. The cavity modes are also Gaussian. And so the overlap integral between the cavity mode, the 0-0 optical mode, and the 0-1 optical mode is a giant Gaussian integral that we can solve analytically. And so after a while, we developed a fully analytical theory of the onset of the parametric optomechanical instability. So these gray lines that are hard to see are the acoustical resonances. The data points are the observed thresholds. Sometimes you get lucky and you're a bit away from the mechanical resonance frequency, then the threshold is higher. But usually the thresholds observed are fairly close to the minimum. And the data matches fairly well, even as you vary the acoustical frequency by varying the modes, axial mode spacing of the cavity. Okay, so analyzing the problem is one thing, solving the problem is another thing. The solution was very simple. Make the mirrors out of zero-dur material instead of ULE. It has a much lower mechanical Q, and therefore the onset of the optomechanical instability is at a much higher power. We also developed a Michelson interferometer to actually measure the motion of the mirror, and we could indeed see the nice Gaussian mode shapes of the acoustical oscillations, matching expectations perfectly. I will not spend much more time. I'll just show you the moment when the zero-door mirror cavity finally reached 300 gigawatts per centimeter squared. We built a vacuum chamber for our cryocooler. And so we're now really excited to put it all together and try it out as a trap. And that's the end of my talk. Thank you so much for listening.
Much. Anybody want to start out with questions?
I have a rather technical question. Could you split your power between multiple longitudinal modes of the cavity to increase the onset power of the
Not
instability?
on purpose, unless Ashwin tells me different.
Do you mean by writing two different?
Like if you used yeah, with an EOM or something to split your power.
I'm not sure why we couldn't do that. I haven't thought very deeply about whether that's the best possibility. But yeah, sorry.
But it's solved now anyway, so
Yeah.
got it.
So
Thanks, Holger. Really interesting talk. Can you talk a little bit about how like the absolute powers you need scale with the electron energy? I know that a lot of people in the cryo-EM community are talking now about building custom scopes at 60 kV as opposed to 200 or 300.
Goes like 1 over beta gamma, which are the relativistic velocity parameters. That's not a very useful answer, but I can't solve it for V versus power in my head right now.
Thanks.
But yeah, lower electron energy makes everything easier.
So is there a possibility of trapping room temperature rubidium in a vapor cell using these techniques?
More power.
That's why we need multiple longitudinal modes.
So my former postdoc, Josef Schwarz, has a project to make these intensities even higher, and he wants to do that to observe the Heisenberg-Euler vacuum nonlinearity. If he is successful with that, then it might actually trap molecules at room temperature.
What is that?
When?
What is the Heisenberg-Euler?
The vacuum has a very tiny nonlinearity where it essentially produces 2 electron-positron pairs. Yeah. The box-like diagram. Yeah. It's never been directly observed, and there are various projects trying to do that with pulse lasers and so on. But the effect that you're looking for goes with the integral power over time. So by having a very bright laser that's on only for a short time, you're not obviously winning. You need a very high average power. And at the crazy cavity workshop, I will say that I believe cavities will get there first.
Thanks, Holger. When you calculated your ionization rates, did you also include nonlinear electronic excitation of the molecules?
I believe the answer is yes. Ashwin can tell you more, but we used this Keldysh formalism that was later upgraded by another Russian whose name I forgot. And the ionization is a 10 or 11 photon effect. So in that sense, it's nonlinear. I'm not sure what other nonlinearity you might be asking about.
I mean, if the resonance is in, no, it's the same. Sorry, like because the photoionization will be at maybe 200 nanometers or something like that. Or and okay, good.
And that's the reason why we think it's a benign thing. But it has never been measured. It has been measured at even higher intensities with pulse lasers, and scaling from that, we should be fine. But sometimes surprises happen. Right? Essentially, the lesson here is with every factor of 2 or 3 of intensity increase, there's a surprise.
Any more questions? In that case, let's thank Holger again.
Thank you, guys.